Now we are going to learn about extreme classification. We use this when we have an enormous amount of labels to label an enormous amount of text. For example, we can use this for labeling a new article with Wikipedia's topic labels, matching web content with a set of relevant advertisements, classifying product description with catalog labels, and classifying a resume into a collection of these job titles. In this course, we are going to transform 250,000 labels into vector embeddings using a publicly available embedding model and upload them to manage the vector index. Then we'll take an article that requires labeling and transform it into a vector embedding using the same model. We'll use that article's vector embedding as the query to search the vector index. In effect, this will retrieve the most similar labels to the article's semantic content. With the most relevant labels retrieved, we can automatically apply them to the article. First, we are going to install Pinecone client. This is client to store our vector embeddings. Then we're going to use sentence transformers and datasets. Then we're going to create an account at Pinecone.io. We're going to go to API keys. We're going to copy our API key. We're going to paste it here into API key, and we will copy this environment. We will paste it into environment. Make sure also that in indexes there is no indexes if you are on the free account, because you can only have one. If we run this, it's going to import Pinecone, and then we're going to just initialize this Pinecone instance. After that, we are going to create a new index in Pinecone where we will store our vector embeddings. So we're going to say index name is equal to extreme-ml, and then if index name not in Pinecone list indexes, so if it doesn't exist, we're going to create it. And we will set dimension, vector dimension, to be 384 and metric cosine. So we can use cosine similarity to measure similarity between the vectors. And then we are going to assign this Pinecone index to this index variable. After that, we are going to load the dataset. So from dataset, import load dataset. And we're going to say, we're going to load this one. So this is a Wikipedia dataset with 200,000 articles and 250,000 different labels for those articles. So we're going to create a new pandas data frame, and we're going to say this data train, we're going to convert that to pandas. And now if we print head, we are going to say to see. It's going to take a minute or two to download all of this, but then we can see this data. So we have article title, then we have content of that Wikipedia article, and we have the labels. As a next step, we are going to convert article content to vector embeddings using this exact model. So we're going to say from sentence transformers, import sentence transformer and import torch. Then we're going to move everything to GPU, and then we're going to say model is equal to sentence transformer and give it the model that we want to use, and device is going to be our device, which will be CUDA. So if we run this, it's going to start downloading the model itself, so we will actually wait for a few minutes again. And then it's going to just print the model. So we have some transformer here with some parameters. We're using birth model, as you can see. Then we have some pooling with some parameters, and we have normalize at the end. After that, we are going to encode articles. So we're going to say encoded articles is equal to model.encode. We're going to pass in content to list, and then we're going to say show progress is equal to true. And then df content vector is equal to pd.series encoded articles to list. So basically, I will show you what we did here. We converted this content of articles to vector embeddings. And then we added, in this line of code, we added that content vector to this data frame. So these content vectors, they represent semantic meaning of this content text of the articles. Now, it actually turns out, if we want to perform search, if we look at these vector embeddings that are embeddings of the content, they perform much worse than if we convert labels into vector embeddings and then search by the meaning of labels. So what we will do now is we will also convert the labels into vector embeddings. As a first step in our data processing, we are going to explode the target column, which is labels. And what exploding does, I will explain now. So I explained it here, but basically, if we have this column in our data, so we have title, some title, content, some content here, and then target, these are our tags. And then we use explode, so we use df explode is equal to df.explode target. Then we're going to get each title and content separated by each tag. So the tags, this list of tags is going to get separated in 3 columns, and each of them is going to have this same title. That's what exploding does. As you can see, if I print df target before explosion, it's going to have these indices, and it's going to have these all of these like lists of labels. But after explosion, if I print df explosion, it's going to have, so for each, so we're going to take a look at right here in this column. So for each of the labels, it's going to have the same index, and then we can see which indexes or indices mean which titles, which indices have each, which content, etc. Now, if we go a bit up here, we're going to see the label embedding is simply the average of all its corresponding article embeddings. So each label can be assigned to multiple articles, and then we take these article embeddings, and then we make average of all of those articles where that label is assigned, and that will be our label embedding. And we will do that down below in this code. So as you can see, we're going to do group by label and define a unique vector for each label. So we're going to create a new data frame that has all of these labels here, and then each label has this corresponding vector, but we are going to calculate these vectors. And then this is like target label. Its label is actually has same values as target. So let's take a look at this line of code. So we have some new variable label vectors is equal to data frame underscore explode, our exploded data frame, group by target. So we're gonna group them by target. And then this piece of code, you can read it here. For each group, calculate the mean of the content vector column, resulting in a mean vector for each label. So for each group, calculate the mean of the content vector column, resulting in a mean vector for each label. So calculate the mean from all content vectors that have this label assigned to them. And now we are going to insert the embeddings into pinecone index. So first we are going to define batch size is 256, meaning that we will go through 256 labels at a time and insert them into the index. So we are going to go for I from 0 to length of label vectors, and we're gonna jump by batch size. So we are going to go from 0 to length, but batch size by batch size, not one by one. And then we are going to find the end of the batch, which will basically be minimum between I plus batch size or length of label vectors. This just ensures that if I plus batch size is greater than length of label vectors, so if the last batch is not a full batch, it's just gonna say the last batch is gonna be till the end of label vectors. After that, we are going to extract batch from label vectors, and we are going to extract it from I to I end. Then we are going to take batch content vector, and we're going to convert that to list. And now we have a list of these embeddings, content vectors. And now we are also getting the list of labels as metadata. So we see that we get some list by these square brackets, and then we say for L in batch label, it's going to go through batch label, and then we're going to say, we're going to create this dictionary, and then it's going to say label, and then the L. If you find any of this confusing, you can also read everything here. And then we are going to create a list of unique IDs for each batch element. So IDs is equal to, and we're going to go from I to I end, and we're going to get the index, and then it's just going to be the index for that particular element. It's going to be unique. And now we are going to combine all of the data, IDs, embeddings, and metadata into a list of tuples. and we're gonna assign it to upsert variable. And at the end, we are going to upsert index.upsert and then vectors to upsert. We're gonna put it into the Pinecone database. Now, if we say index.describe index stats, we're gonna say that dimension 384, index fullness 0.7, namespaces, this doesn't matter, and then vector count 256,000. What this application allows us to do is take a new article text, convert it to an embedding, and then compare this to embeddings in our Pinecone database to find the closest vector embeddings, and those will be the most similar labels. That's how we pick labels for that particular text, article text. So now that we have all of these labels in our Pinecone database, we can take another article text and convert it to an embedding, and then compare that embedding of that article text to label embeddings, and we will find the closest vector embeddings. And then that means that that article text is most corresponding with those closest vector label embeddings. This will allow us to quickly find labels for our articles. So to test this, we are going to load this test dataset. As you can see, we have title, content, and then target. These are labels. And then we are going to define a few functions here. The first function is select test article that just takes an index, and it's going to return article with that index, first 1,000 characters, and it's going to say title of the article, content of the article, and original labels of the article, and it's going to print it. So the second function is query Pinecone. It's going to take in the article and top K. I'm going to explain what top K is. So first we're going to create embeddings for text test article. So xq is equal to model.encode article.content. We're going to pass in the content of the article, and then we're going to convert it to list, so we have list of embeddings. And then we are going to query Pinecone for labels. So results is equal to index.query. We're going to pass in our list of embeddings, and top K is equal to top K. So we're going to find the three most similar embeddings. That is the three most similar embedding vectors for labels. So we're going to find the three most similar labels and include metadata is equal to true. And then we are going to print those three most similar labels. Now let's see what we got here. So we're going to say article is equal to select test article 524. So 524 is the index of the article we're going to select. And then we say that query article is going to be, content is going to be like this content. Original labels will be these labels, audio codec, MPEG-4, etc. And then title will be MPEG-4. And then if we query Pinecone with this article, and we're going to find the 10 most similar labels, we're going to see that the most similar labels are container formats, MPEG, free video software, etc. We can also try some more queries. So article is, we're going to choose article 354, which is different. This is the article content. This is the original article labels. And then if we run the query labels, the query Pinecone, we are going to see that the labels we retrieve are similar to these original labels. And you have one more example down below that basically says the same thing. It also retrieves the similar labels to this article text. And now we can check out the summary of this project. We demonstrated a similarity search approach for performing extreme classification of texts. We took a simple approach representing labels as average of their corresponding texts, vector embeddings. In classification time, we match between a new article embedding and its nearest label embedding. Our result example indicate the usefulness of this approach. You can play with this, change code a little bit. You can post your code or whatever you did in this group on School. And thank you for attending this course.